One, one, two, two, three, three. The three laws of thermodynamics. Okay, so we're going to talk about the three laws of thermodynamics here. And in these three laws of thermodynamics, a lot of it does indeed revolve around this equation, PV equals nRT, or if you'd like, NKT. Where, as we will see later on, we're actually going to spend a whole slew of videos just talking about this idea here of PV with pressure volume graphs. It's a very important idea. We'll see that in later videos. But right now, this is just an overview of the three laws of thermodynamics. Now, you would think, being the physicists that we are, that if we had three laws of thermodynamics, we would count them 1, 2, 3. But we don't, because, why not? We actually start at 0. The 0th law of the thermodynamics is actually the law that physicists forgot about. It wasn't until after we had the first and second laws that mathematicians came around and said, hey, your laws only work if you're making this assumption, and if you don't explicitly state this, then we could break physics if we wanted to. This wasn't cool for physicists, so they said, watch this, and they went back and made the 0th law. And this law is actually really straightforward. Imagine you have objects A, B, and C. If the temperature of object A is equal to the temperature of object B, and the temperature of object B is equal to the temperature of object C, then we could just state that the temperature of object A must then be equal to the temperature of object C. Yeah, that's it, a transitive property. That is the 0th law of thermodynamics. That's why we didn't actually make it in the world of physics initially, and why we kind of forgot about it, because yeah, if all of these are equal, no duh. From a physical standpoint, the temperatures are just even. There will be no heat flow. But from a mathematical standpoint, that explicitly needs to be stated. So there it is to make all the mathematicians happy. That's the 0th law of thermodynamics. Let's actually get into something that looks a little bit more interesting and means something a little bit deeper on the physics level. For the first law of thermodynamics, we have the following. We have that the change in internal energy of an ideal gas is equal to Q, which is some amount of heat. This heat energy can either be put into the system or taken out of the system, plus some amount of work. And this work can either be done on the system or done by the system. In some textbooks, you may see that this positive sign here will pop up as a negative. We're going to keep it positive for us. There's a reason why. It has to do with conventions. It goes all the way back to what we're going to see in a little bit with these PVs going on, because that's how we're going to get this work coming out anyways. We'll see that in future videos. But we're going to keep it as delta U equals Q plus W, okay? And it is important to remember that this U we had here in our last video, U is equal to the Augy-Dinch equation, as I like to call it, but it's just a internal energy of an ideal gas. That's the 3/2 nRT. If we have a delta U, like we have here, then technically this is going to become 3/2 nR delta T, because we have to have a change somewhere in there, okay? And a change of temperature will give us a change of this internal energy. And that will equal Q, which sometimes it might be given to us as just a quantity like 600 joules, or sometimes it may be given to us as an MC delta T. Remember that from calorimetry. And then we've got some amount of work here. And this work, we might have to use a graph in order to find it. So there's a lot of stuff going on with this equation. This equation right here, this first law of thermodynamics, this is the bread and butter of thermodynamics. This is what we're going to be spending almost all of our time on. It's super duper important. We're going to spend a ton of time figuring out how to look at graphs in order to figure out the amount of work. We're going to spend a lot of time analyzing, what value this work should have, and it should be positive or negative. We're going to spend a lot of time looking at changes in temperatures. That's what this is all about. That's why we had to do all the calorimetry. That's why we had to do all of the kinetic molecular theory of gases and molecules. Like, we had to get to this. So this is what it's all about. This is the equation you need to know. Burn this into your retinas and your cortex in your brain. Like, that's what you need, okay? Right there. The other thing that we would need in our actual third law, which is number 2, because, counting is hard, is dealing with entropy. And we're going to talk about this in detail in a much later video. But essentially, the second law of thermodynamics is as follows. Some change in entropy, which can also be thought as chaos in a system, is equal to Q, which is a heat change, so heat entering or heat energy entering in or leaving a system, divided by an average temperature of that process. And we're going to talk about this, like I said, in much more detail later on. Right now, the biggest thing to recognize is that this needs to be in Kelvin. It must be in Kelvin. And this has to be a reversible process. The process needs to be able to go in both directions when we look at our graphs. We'll see what that means later on. Like I said, we're just covering a brief overview right now, and this is the equation that we will need for this. We'll talk about the arrow of time, what entropy and chaos actually is, and how to think about it in a future video. So stay tuned for that, okay? So there we have it. Those are the 3 laws of thermodynamics, 0, 1, and 2, kind of named like an array. We've got a transitive property, just mapping temperatures. The first law of thermodynamics, delta U equals Q plus W, which is the big deal of the day. And then our second law of thermodynamics, delta S, or some change in entropy, equals Q over T average. And with that, this introduction is complete. In our next videos, we'll be diving into this first law of thermodynamics because, like I've been saying, it is the most important thing to talk about here. So stay tuned for that. And until next time, adios and take it easy.